again, we have a charged particle moving through a uniform magnetic field. Okay, and what do we know about charges moving through a magnetic field? They'll feel a force, and the force is determined by this equation involving the cross product. We know that because we have a cross product, the force is perpendicular to the velocity. Well, if the force is perpendicular to the velocity, the acceleration is also going to be perpendicular to the velocity. Okay. You may recall from your previous physics course that when the acceleration is perpendicular to the velocity will certainly change, but the speed, as it turns out, will not change. Okay, so this seems a little strange. We have a net force acting on this charged particle. It's accelerating, and yet I'm telling you that the speed does not change, even though it's accelerating. Oh, but the reason it's accelerating is not because the speed is changing, but because the direction of the velocity will be changing. So if you put all this together, you have an acceleration perpendicular to the velocity, and constant speed, meaning the speed of the charged particle will not change. Then you can deduce that there will be a certain kind of motion that the charge will be undergoing in the magnetic field. Now we have to add one more condition just to make it a little bit easier to understand. We'll make a choice that V is perpendicular to the magnetic field. So here's a velocity vector, this green vector. It's pointing in the plane of the screen. The magnetic field, these X's are pointing into the screen. So V is perpendicular to the magnetic field. We're making that choice. It doesn't have to be perpendicular. It's not like F is perpendicular to V. That is a consequence of the cross product. That's always true. But look, you can fire these charged particles in whatever direction you want relative to the magnetic field. If you make them perpendicular, it turns out these charged particles will execute circular motion. Okay? What happens if the velocity is not perpendicular to the magnetic field? I'll tell you shortly. But let's consider the case where V is perpendicular to the magnetic field. The charged particles will move in circular motion. Okay, let's look at the consequence of that. So we know that from Newton's second law, the force is equal to mass times the acceleration. And I've written that equation in magnitude form. So this is the magnitude of the force. And here's the magnetic force, the magnitude of Q, magnitude of V cross B. On the other side, we have mass times the magnitude of the acceleration. Oh yeah, but for circular motion with constant speed, you'll recall the acceleration is V squared divided by R, where R is the radius of the circle. Okay, so if V is perpendicular to B, that's a choice. The angle is 90 degrees, and the sine of 90 degrees is 1. And we leave the right-hand side as it was. You'll notice there's a partial cancellation of V. V cancels partially with the V squared on the other side. If you solve for R, the radius of the circle, you get mv over magnitude of Q and magnitude of the magnetic field B. It's important to remember you're always taking the magnitude of the charge. If you have a negative charge and you don't take the magnitude, you'll end up with a negative radius, which doesn't make sense. So make sure you use the magnitude of the charge. Okay, so let's calculate the frequency of the motion. The frequency is just going to be the speed divided by the distance you go once around the circle, which is the circumference of the circle, which is 2 pi r. Okay, so if you think about it, this quantity will have units of 1 divided by time. Well, that is the frequency. So with our expression for r, if I substitute that in here for frequency, We see the frequency, expression for frequency is magnitude of Q times B divided by 2 pi times the mass. Okay, so let's use this to analyze, to solve a problem. And this is a nice problem because it combines some things that we learned about earlier in a previous chapter, where we have charged particles accelerating through electric fields over electric potential differences. It combines that with motion of charged particles in magnetic fields. So here's the picture describing the problem. We have a metal plate which is held at 0 volts, and another conducting metal plate which is held at 500 volts. So we have a parallel plate capacitor, and we know that there will be an electric field between the plates that goes from the high potential, the right side, over to the low potential side, which is the left side. So think about that. The electric field is pointing from high potential to low potential. The electric field is pointing to the left. Got it? So if the electric field is pointing to the left, why is this particle moving to the right? Oh, it's an electron. And electrons are negatively charged particles. And negatively charged particles will feel a force in the opposite direction to the electric field. So if the electric field points from right to left, the force on the negatively charged electron will be from left to right. So let's say the electron starts off at rest at this position, and then it accelerates through this 500 volt potential difference, and then there's a little hole in the plate. Okay, so it starts from rest, it accelerates, it undergoes linear motion, and then it goes through a little hole in the plate, and then there's no electric field outside of the plate. However, we've arranged it so that we have a magnetic field, and the magnetic field is pointing, as you see by the X's, is pointing into the plane of the screen. So if you think about what happens, as soon as the charge enters the magnetic field, its velocity is pointing to the right, it's moving in this direction, but it will feel a force. Okay, think about what direction the force should be going in. Velocity is to the right. The magnetic field is into the plane of the page. Use the right hand rule. Fingers of your right hand in the direction of V, that will be pointing to the right. Curl your fingers in the direction of the magnetic field. That's into the screen. Your thumb points up if you do that right. Oh, but it looks like this charge is being deflected downwards. The force is initially pointing down to deflect it in this direction. Why is that? Oh, again, it's an electron. It's a negative charge. So when you calculate the cross product direction, the force will be in the opposite direction, so it will be pointing down. Okay. So the electron accelerates from rest through this potential difference. It's injected into a uniform magnetic field. Once inside the field, it completes half a revolution in 2 nanoseconds. What's the radius of its orbit? Okay, to solve this problem, the first thing we're going to do is to find the speed that the electron has right at the point where it leaves the electric field between the plates and enters the magnetic field region on the right-hand side of the right plate. Okay, to do this, we'll use conservation of energy. So the initial point is here. The final point is here, right when it goes through that hole. So initial kinetic and potential energy is equal to final kinetic and potential energy. Kinetic energy is a half mv squared. I is for initial, F is for final. Remember the relationship between electric potential energy and electric potential V, the voltage. It's U is equal to Q times V. So U sub I is Q times the initial potential. That's 0 volts. Okay. And note that the initial speed, v sub I, is also 0. That's why you have a 0 plus 0 here. On the other side, well, we don't know v sub f. We want to find that. And what is, well, I have to be careful about using saying v. I mean, little v is the speed. Capital V is the voltage or electric potential. V sub f, big V, the voltage, the final voltage, is of course 500 volts. Positive 500 volts. Okay, so what you can do now with this equation is solve it for V sub f, little v, the speed, the final speed. You should find that it's a square root of 2 times E times the final voltage divided by the mass. Okay. Now you might be a little surprised. You might expect there to be a negative sign here. Shouldn't I have, when I bring this term over to the other side of the equation, doesn't that introduce a negative sign? Yes, it does. I would have negative Q here, but instead I write E. Now you might want to have a pen and paper handy right now to write this down. Okay, Q, little q, is equal to negative E. E is the magnitude of the charge on an electron or proton. The charge of an electron is negative E. Because Q, the charge of an electron, is negative E, and there's another negative sign that comes from bringing this term to the other side of the equation. The two negative signs cancel out. You might want to just write that all out if you have trouble following what I'm saying. But in the end, what you should discover is you have the quantity E here, the elementary charge. It's the magnitude of the charge of an electron. Why am I making such a big deal about signs? Because you have to make sure that what you're taking the square root of is a positive quantity. You don't want to take the square root of a negative quantity. And you don't have to. The negative signs all cancel out. Okay. So when you do this calculation, for some reason this 2 has become a 1. I don't know why that is. I think that's just a typo. This is the charge. This is the final voltage. Look up the mass of an electron. And when you do that calculation, you get a very high speed, 1.33 times 10 to the 7 meters per second. It's a good fraction of the speed of light. Okay, so let's move on now. What do we know here? We know that the charged particle is undergoing circular motion in the magnetic field. Okay, and we know that it takes 2 nanoseconds to go through a semicircle. We're given that information. Now, the period is the time it would take to go through a full circle if it was possible to go through a full circle. So the cyclotron period, the period of the motion of the charge in the uniform, undergoing circular motion in the uniform magnetic field, the period of the period of that motion will be twice the time it takes to go through a semicircle. So that means it will be 4 nanoseconds. The frequency is, the cyclotron frequency is 1 divided by the period. So capital T is the period, that's the 4 nanoseconds. And do that calculation, you get 2.5 times 10 to the 8 hertz. Now we have an expression for the cyclotron frequency. And in terms of Q, B, and the mass of the particle, if you solve for the magnetic field, solving this equation, okay, just rearrange it to find B. It's 2 pi mf divided by E. Substitute in the numbers, and this is what you get. 8.5 times 10 to the minus 3 Tesla, Finally, the radius, substitute it back into this equation, you'll get 8.5 millimeters.